Energy density. Part 1. Imagine we have a volume of fluid, say a gallon of milk or 1 liter. So we take this 1 liter bottle at some initial height and simply drop it. Initial speed is 0. We release it. It falls. And so our liter bottle falls down. Its final position is right before impact with the ground. So Y final, let's say, is 0. And the V final is the maximum speed it has right before impact. So we know we've descended in height, therefore we've lost gravitational energy. PE gravity goes down because height initial is greater than height final, losing gravitational energy with losing altitude. But if one form of energy goes down, we know another form of energy has to increase. And since the velocity increased, the kinetic energy increases. So it's a negative PE gravity, or negative gravitational energy change. Lost sans minus this amount of potential energy is the increase, positive delta KE. Losing gravitational energy, increasing kinetic energy. Putting in the variables in relationship form, a loss of gravitational energy means that mass, thanks to gravity, lost height. And that's equated with the kinetic energy, the speed squared times the moving mass. But this is the potential energy part of this volume, and therefore the kinetic energy also part of that volume. This 1 liter, this volume, this liter bottle, it's not the gravitational energy of a water particle, or a liquid particle of any sort, or any handful of particles, as we've been dealing with throughout the semester. We're not talking about a few particles or a particle. We talk about a volume when it comes to fluids, a volume of gas, a volume of liquid. It's much more practical that way. So this is a change in gravitational energy for the whole volume, such as for the whole liter or for a whole gallon. Therefore, it's the kinetic energy gain for the whole liter. So it's the mass per volume, energy per volume, therefore mg delta y divided by the volume, and the kinetic energy per the volume. Now mass per volume is mass density, or density for short. We use the Greek letter rho, that funky P is the Greek letter rho, to symbolize density. Be familiar with mass per volume being symbolized by the Greek letter rho for density. In a sense, that's the heart of this chapter. So replace mass per volume with density, with rho. So now it's negative rho g delta y for gravitational energy density, for the gravitational energy per volume. And for the kinetic energy density, the kinetic energy per volume, it's 1/2 rho delta v squared. Again, these are energy densities we're talking about now, energies per volume. So it's an energy density equation, or conservation of energy density. The loss of gravitational energy density is accounted for by the gain of kinetic energy density. Let's say instead the liter bottle hits your foot. So its final speed is 0 in this final condition. Well, it still fell some height and then hit your foot, but your initial speed is 0 and your final speed is 0, so we didn't change kinetic energy. The change of energy is a thermal energy. Your foot warms up, the liter bottle warms up, the sound that's created, the sound eventually becomes a change in the air pressure. The sound is a change in the air pressure. Sound becomes heat. Sound becomes heat in the time it takes for an echo to die. So we lump into thermal energy sound, heat, friction, resistance, drag, general losses of energy of all types. So this is the thermal energy that's been gained into your foot from the falling of this bottle. So the loss of gravitational energy is the gain of thermal energy per volume. So it's a gravitational energy density decrease and an increase of thermal energy density. Here's a waterfall Water's falling over a cliff. How do we track the energies of this waterfall? Well, by how much volume of water is falling over. Let's say the volume of water is measured in liters. It's the same thing as saying we have a liter bottle falling, as we just did. As we discussed, liter bottles falling would be an example of energy changes. So this waterfall can be consisted of many, many liters of water falling. Those liters of water are still descending in height, so that's a loss of gravitational energy per volume, for the volume of the waterfall measured in, say, liters or gallons, or whatever your choice of volume is. So this is a decrease in gravitational energy density for the waterfall, for every particular volume that falls over. And that's equated by the increase in the speed, the increase in the kinetic energy per the volume we're measuring. So again, we have the same gravitational energy density equation, equaling the increase in kinetic energy density. What's the equivalent of hitting your foot? Well, the water smacks into the rocks. Those liters of water smack into the rocks, and again, warm up the rocks, warm up the water. They make noise and sound, the friction, resistance, all this is thermal energy. It's a thermal energy density, a thermal energy per volume of water we're discussing. So we add this to our energy density equation. Conservation of energy is the loss of gravitational energy, and the gain in kinetic energy density, and the gain in thermal energy density, just as before. What are the units of energy density? Well, it's energy per volume. Energy's SI units, System International, is joules. Per the volume, our volume is still meters cubed. That's our System International, our MKS system, meters, kilograms, seconds. So it's joules per meters cubed. Volume has to be measured in meters cubed. And density, therefore, is in kilograms per meters cubed. End of part 1.